Greetings and salutations to one and all. We are from Team Grid IQ Pro, representing NIT Raipur. So the problem statement which we have chosen is that renewable energy monitoring system for microgrid. So the problem statement which is we have chosen is that microgrid efficiency has been decreased in the rural places. In order to increase the air efficiency, we have provided with a solution called Grid IQ Pro. Grid IQ Pro redefines a microgrid generation and distribution of the renewable energy with intelligent autonomy using IoT and AI platform. Here we are using a distributed node approach, and the AI predicts and balances our node. The critical nodes are prioritized first always, and non-shedding is informed in advance through SMS, and resilient microgrid ensures reliability. Interactive multilingual web pages empowers our users. So moving on with our system architecture. In our system architecture, we are having three smart nodes and a one local gateway, which is going to be our brain. So in our edge smart node, we are having generation node. And in our generation node, we will be having our voltage and current sensor ESP32, where in our ESP32, we'll be having a tiny ML model, which is used for the fault detection within 1000 milliseconds. And in our storage node, we are having the same kind of architecture, which is connected to our battery. So from the generation node, using the LoRa communication, we'll be sending the data through our brain, local gateway brain, which is none other than our Raspberry Pi. And in our Raspberry Pi, we'll be running all these modules. Well, if we wanted to have it very clearly, in our weather and power forecasting, we'll be getting the data from the generation node. And for our SOC prediction, we'll be getting the data from the storage node. Once these data are fed into it, this model creates an output which will be sent to our major game changing factor unit called power control unit. In our power control unit, we'll be having battery SOC scheduling and optimal load scheduling. So these data are sent back into the load node, where we'll be having a ESP32, which will be controlling the non-critical load and the critical load, where it will be prioritizing only the critical load according to the demand and according to the power consumption and also the power generation. So after once all this done, in order to store our data, we'll be moving on to our cloud platform. In our cloud platform, we'll be having our cloud database for storing our data, and we'll be retraining the models which we are using the data which we have collected from all these sensors. And this is our technological stack. And you can, well, moving on further, here it's our feasibility. In our technological feasibility, we'll be having IoT and sensor microprocessor, and we are also using for it is renewable generation and reliable power anytime using AI for the predicting approach. The major challenges we face in our rural area is the connectivity issues, and also the limited processing power. Hardware and sensors failures can be happening in some other in will be happening in times, and sensor calibration is also very much needed, and the operator training. In order to mitigate all this, we will be overcoming this by using the LoRa and storage backup. During the offline, we will be storing the data, and we'll be storing in the data locally. Once network connectivity is achieved, we'll be sending the data back into our cloud. So by this, we are ensuring the connectivity issue, and we are having the modular approach of sensor nodes. For better understanding of our solution, you can feel free to go through our Google Drive. And so economic benefits, as mentioned in the problem statement, how we achieving the 15% efficiency in our microgrid. So we are achieving it by recovering the lost generation from the renewable energy, which is approximately gain of 5%, and the smarter battery dispatch using our SOC modeling, we are gaining a 4% gain, and the reduced distribution losses of 3%. And these are the things which will be compiling up to make a 15% implementation. And in our environmental benefits, we are having the more renewable utilization and longer battery life, which increases the life of the battery, and which are providing a less CO2 footprints and the market problems. So we can see the who are the big, we can see our big players, which are Siemens and ABB, etc. How we different from our market players? We are providing the solution in a very less expensive, and we are having a closed modular approach, which is standing out from our marketplace. And we're moving on to a unit economics. We are having our hardware part, which is ranges around 12,000, and the gateway services which we are providing is around 5,000 to 6,000, and web services is around 3,000. So it comes under the minimal cost. And So this is our research references. And before concluding my speech, I wanted to share my web dashboard. So here is our web dashboard. So here we, as I promised before, it's going to be our multilingual approach. So in our multilingual, here you can see it is going to be English dashboard, and it can be also be Hindi dashboard, and it can also serve as a ODI dashboard. In our ODI dashboard, you can see how it is being done. Flawless, right? So once let us get to what is in our dashboard. Let's get started. So in our dashboard, we will be showing what is the weather condition and solar generation and battery health. So these are our predictive graph. So you can see what is the power being generated, and we can see the fault approach also. In our fault, we will be prioritizing and we will be seeing what is our fault is. So if we are seeing the voltage fault, if I wanted to off it, so there is a pop-up, I can off it. So this is how our dashboard works. And so this is our dashboard works, and thanks for this giving this opportunity to share our idea.